Video is accompanied with our paper submitted to IEEE Access with the title 15 gigabit per second Double SHA-256 Hardware Architecture with Compact MessageExpender for Bitcoin mining. We are from NICE in Japan and from UIT in Vietnam. This research is supported by Japan Science and Technology Agency's Presto Grant Number 2019 A039. And this is the agenda, which includes the research background, the proposed work, evaluation, layout chip, conclusion, and future work. In the background, we briefly explain the Society 5.0, blockchain technology, Bitcoin mining, and SHA-256. We spend quite much time for the background because we think that it is important, and we hope to bring you a sufficient overview about this research field. Instead of the proposed work, we show the overview of our proposed architecture, Double CME SHA-256, and then we go in detail about CME algorithms and circuits. In the aspect of result, we evaluate circuit area and power consumption in both aspects of theory calculation and practical experiment. Firstly, let's go to the background, Society 5.0. As you know that our society has gone through 4 generations. Society 1.0 or hunting and gathering society. Then go to Society 2.0 or agriculture. Then go to Society 3.0 or industrial society. And now we are in Society 4.0, which is also known as the information society. Recent years, Japan and other developed countries has laid out research platform for Society 5.0, which is also known as the Super Smart Society. In Society 5.0, a huge amount of information from sensors in physical space is accumulated and stored in the cyberspace. In cyberspace, this big data is analyzed by the AI engine, and then they fed back the result to the physical space in various forms of application and service to benefit human life. For example, the self-driving car, robots, healthcare system, and so on. For achieving high efficiency, data used by these apps and services should be shareable in a secure manner. Therefore, developing a secure and shared cyberspace is very important. With our current technology, blockchain is a candidate for securing such a shared cyberspace. The core operation of the blockchain is the SHA-256. In addition, the SHA-256 is also employed to secure data in the physical space. Therefore, developing a compact SHA-256 hardware circuit is a research trend. And this slide illustrates a simple decentralized blockchain network in which data are decentralized stored in many computers all over the world. In each computer, the data is stored in a chain of blocks we call as the blockchain ledger. And blocks are connected via the hash value. To be able to write a data into the existing blockchain ledger, the miner must work hardly to find the valid hash values. And a famous example that employing blockchain technology is cryptocurrencies, such as the Bitcoin, Ethereum, Dash, Ripple, and so on. And these cryptocurrencies are peer-to-peer payment networks with no intermediate financial institute such as the bank. And among these virtual currency, Bitcoin is the most popular and the biggest one in the market. However, the biggest problem of the Bitcoin is electricity energy consumption, as you see in this graph. The electricity consumption of the Bitcoin network recently it reached to 75 terawatt hours per year. To see how large it is, let's look at to this figure that shows the electrical consumption report on July 2019, and you see that the electrical consumption of Bitcoin is surpassed. It means it's much more than the electricity consumption of countries such as Switzerland or Greece. Therefore, reducing energy consumption of Bitcoin network is important. Recently, Intel, IBM, and other R&D research centers have invested on researching and then registering patents for their research in this field. The question is, why Bitcoin network consumes such high electricity energy? Here you see that most of energy consumption of Bitcoin network come from the mining process. The Bitcoin follows the proof of work consensus, in which the miner must work hardly to find the hash value for a new block. And this slide illustrates the mining process of a Bitcoin network. It follows 3 steps. The first, it calculates the Merkle tree hash of the data, and then it forms the header, and then compute the Double SHA-256 to find the valid hash value. To find the valid hash meet the target, so it changes the nonce value in here, and the nonce here will be changed until the valid hash is found. It is said that the total Bitcoin network needs about 10 power 20 times of repeat the double SHA calculation to find a valid hash for a block. And that is the reason why Bitcoin consumes such huge amount of electricity. Therefore, reduce the power consumption of Double SHA-256 is an important factor to reduce the electricity consumption of Bitcoin network. And this is an example of hardware resource need for computing Double SHA in Bitcoin mining pool. You see that a lot of GPUs are piled up again and again in a mining pool. And from now, let's go inside the computation of Double SHA-256. It needs 3 individual SHA-256 circuits. Input of the Double SHA is the 1024 bits header. And the first SHA circuit is compute the hash for the first 500 tails input data. And the next SHA circuit is compute the hash for the last 512 bits input. And the final SHA circuit is to compute the double SHA for the previous result. And you see inside each SHA circuit, there are 2 processes we call as the message expander and message compressor. And this slide explains the detail of calculation inside each SHA-256 circuit. The 512-bit input data are divided into 16 words of 32-bit data, denoted as the W0 to W15. And from this input, the message expander process or ME process, it will calculate the words from W16 to W64. And finally, we have 64 words of 32 bits data. And from this data, the MC process will make the calculation to find the final hash value. And algorithm 1 and algorithm 2 respectively show the algorithm of the ME and MC process. And both processes repeat the calculation 64 times, 64 loops. And in this research, we focus on optimizing the hardware circuits of the ME process. Therefore, we will explain more detail about the ME process. You see here, look at this equation. You can see that to calculate 1 word WG in the ME process, the conventional ME process must follow this equation. In here, they need 3 32-bit adders, and then the sigma 0 and sigma 1 function, in which the sigma 0 and sigma 1 function is calculated in this equation. And finally, we have the conventional computational circuit to calculate each value, each work of the ME process is shown in here. And in this research, we optimize this calculation by utilizing the characteristic of the input data. Let's start to mention about our proposed work. This slide shows the overview architecture of our proposed Double SHA-256 circuit for Bitcoin mining. It includes 3 individual SHA-256 circuits, which I will call them the SHA circuits for shortly. Notice that the nonce field is incorrect until the valid hash is found. As a result, input data of the SHA block 1 is not changed, while the input data of SHA block 2 and block 3 are frequently changed. Because we target both high processing rate and low hardware cost. Therefore, we propose the SHA block 1 as the resource sharing architecture and block 2 and block 3 as the fully unrolled data path architecture. The SHA block 1 generates 256 bit hash every 64 clock cycle, while the block 2 and block 3 generate 256 bit hash every clock cycle. Overall, the entire circuit generates 256 bit hash every clock cycle, which is equivalent to processing rate of 15.36 gigabit per second in 64 MHz operating frequency. To further reduce the hardware cost and power consumption, we propose the Compact MessageExpender or CME method in the SHA block 2 and SHA block 3. Let me explain about the Compact MessageExpender or CME methods for SHA block 2. Firstly, let's look at the input data. It includes 32 bits of previous hash, 32 bits of time, 32 bits of the bit target, and 32 bits of nonce, which are equivalent to value of W0 to W3. The remaining 384 bits of padding and length, they are equivalent to value of W4 to W15, in which W4 and W15 are constant. The remainders are on 0. By utilizing the zero characteristic of the input data, we can optimize the calculation of the CM2 methods. For example, to calculate the W16, because of W14 and W9 are on 0. Therefore, we can optimize the calculation. Finally, to calculate W16, it only needs one 32-bit address and one sigma 0 function only. So we can reduce the hardware cost. To understand more about our proposed work, yes, let's go to the section.
Similar to W16, we finally analyzed the remaining 32-bit words. The final result, the analysis are shown in this figure. So based on the reduction of computations, we propose compact computational circuit for Compact MessageExpender. For example, so compact, so this is a short computation only contain the one 32-bit adder and the one sigma 0 functions. It's also similar to short computation. But however, from the route 31 to 63, because it cannot be optimized, the computation circuit will not change. To present hardware design of Compact MessageExpender, it can be seen that we classify the hardware Compact MessageExpender based on the characteristic of data path bit width into 3 phases. So in phase 1, the data path bit width only has 128 bits from Route 4 to Route 19. In phase 2, the data path bit width increased from 160 bits to 480 bits from Route 20 to Route 30. In phase 2, the data path bit width decreased from 512 bits to 30 bits from Route 57 to Route 63. To understand why the data path, we show you the detailed data flow. Specifically, the registers only store 32 bits needed to calculate for the current route or the next routes. In addition, the 32-bit redundant words will be removed. I want to present the Compact MessageExpender algorithm for SHA-256 State 3. At SHA-256 State 3, the first 256 bit is the output of SHA-256 State 2, and the last 256 bit is the back-end bit. In particular, the majority of 256 bit back-end is almost zero, similar to Compact MessageExpender of SHA-256 State 2. The basic idea is to improve the calculation of 32-bit words from Route 16 to Route 63. For example, at the computation of 16, we also remove the sigma 1 of W14 and W9 because W14 and W9 equals 0. So after analyzing for the remaining routes, the result I show in this figure, so also similar to the Compact MessageExpender for SHA-256 State 2. Short circuit computation are also proposed based on the algorithm of Compact MessageExpender SHA-256 in say State 3. This one, I also would like to present the hardware design of Compact MessageExpender. So it can be seen that we also classify the hardware Compact MessageExpender based on characteristic data bit width into 3 phases. In phase 1, from Route 1 to Route 23, they also has 256 bits, and from the phase 2, they also have increased the number of bits from 256 to 480 bits. And the phase 3 is also similar to the phase 3 of Compact MessageExpender for stage 2 is decreased from 480 to 3. To understand adjustment of bit bandwidth is also similar to their bit bandwidth database in the Compact MessageExpender for SHA-256 State 2. In this section, we want to talk about the evaluation of hardware cost and power consumption. Firstly, to introduce the evaluation in theory. In this section, we review the related two architectures. The prototype architecture is almost basic architecture to achieve high performance for Bitcoin mining hardware. In particular, SHA-256 State 2 and SHA-256 State 3 are fully enrolled database in prototype architecture. And a second part is the optimized architecture. Here, the optimized architecture is a set of best innovations from related system to improve prototype architecture. Finally, this is our proposed architecture. So the evaluation showed that our proposal can reduce significant some hardware resources. Then we conduct the synthesize in ASIC 180 nanometer technology. The result of report show that the area of proposed architecture is significantly reduced correctly. The area of proposed architecture decreased 13.9% compared to the optimized architecture and 17.6% when compared to prototype architecture. Speaking of the reduced area, our proposed architecture also significantly reduced energy consumption, particularly the energy consumption of proposed architecture reduced 9.5% compared to optimized architecture and 15.82% compared to the prototype architecture. Moreover, we have successfully decided for proposed architecture in ASIC CMOS 180 nanometer technology. So the chip size is 5.9 millimeter times 5.9 millimeters. Ultimately, we want to introduce the conclusion and future work. So we have proposed the Compact MessageExpender SHA-256 Hardware Architecture for Bitcoin mining, and the Compact MessageExpender algorithms helps to reduce the circuit error and power consumption in the range from 9.5% to 17.6%. The chip has been successfully laid out in 180 nanometer technology and 60 megahertz maximum data rate from 15.36 gigabyte per second. In future work, we will develop low-cost, low-power consumption SHA-256 for multiple applications.